To our Honorable Chief Guest, Dr. B.D. Kulkarni, respected Principal, Dr. Arya Jagirdar, sir, teachers and all my dear friends.
Today we have among ourselves Honorable Dr. B.D. Kulkarni sir, CSIR Distinguished Scientist and the Distinguished Professor MD ACSIR NCL Pune for his expert lecture on sustainable chemical engineering and future.
No procession is complete without the blessings of God Almighty. Our founder father late Padma Shri Dr. Vittalrao Vikhe Patil. So I request all the members on the dais to please proceed for puja and also request our Honorable Chief Guest to kindly enlighten the line.
Thank you sir. Thank you, sir. Now I would like to request upon our respected HOD sir, Dr. R.W. Gaikwad, to convey the welcome speech and introduce our honorable chief guest to the audience.
Hello. Good morning to all. Respected Dr. B.D. Kulkarni sir, chief guest of today's function and the most valuable personality in PREC. On behalf of Department of Chemical Engineering, Rural Education Society, staff, student and management, I welcome you sir to this institute. We are fortunate enough to have such a towering personality in chemical engineering, Honorable Dr. B.D. Kulkarni sir. We are trying since last 4 or 5 years to call sir to deliver a talk to you, you actually, and today the day have come. Sir has very distinguished personality. He is a scientist of CSIR, distinguished professor and dean, Engineering Sciences, ACSIR, National Chemical Laboratory. He has completed his PhD in 1978 and MTech 1972, BTech 1970. He has very vast experience in the field of chemical engineering all over the world. He received many honors and awards. In 2007, J.C. Bose Fellowship, then Fellow of TWAS, the Third World Academy of Science, Trieste, Italy, then Award of Federation of Indian Chamber of Commerce and Industry, then Chemtech CEW Award for Outstanding Contributor in 2000, Best Scientist of the Year in NCL Research Foundation National Chemical Laboratory Pune, Fellow of INSA, the Indian National Science Academy, which is one of the most prestigious, then Shanti Swarup Bhatnagar Prize for Science and Technology, Engineering Science and Technology, Council of Scientific and Industrial Research, New Delhi, India. Fellow of Indian National Academy of Engineering. UDCT Golden Jubilee Visiting Fellow of UDCT Mumbai. Ardeli Award for Excellence in Basic Research in Chemical Engineering. Fellow of Indian Academy of Sciences. Fellow of Maharashtra Academy of Sciences. He also received Amar Daikem Award by ISCHE. Then he also received in 1980 Medal of Young Scientist by INSA, that is Indian National Science Academy. He served many bodies like Indian Academy of Engineering, then Society of Scientific Values, New Delhi, Indian National Academy, the Asia Pacific Chemical Reaction Engineering Working Party, Confederation of Indian Industry, ISCRE, then member of International Advisory Panel and Editorial Board, Chemical Engineering Sciences, Elsewhere Science, member of International Advisory Body for American Chemical Society. The other nominations are, in 2007, nominated as one of the directors on the board of directors at Hindustan Organic Chemicals Limited, Mumbai. Nominated as HOCL non-official independent director, Hindustan Fluorocarbons Limited, Hyderabad. Nominated as a member of Research Advisory Council at NTPC, New Delhi. Board of Director of High Tech Biosciences, Pune. Member SAC MOPNG at MOPNG. Nominated as a member of Research Advisory Council, NTPC, New Delhi. Chairman Selection Committee for Selection of Directors, ARCI, Hyderabad. Member High Level Committee of Distinguished Chair Professor, Director of Science and Technology, New Delhi. He has got 357 research publications in international journals. He authored 21 patents, 66 PhD awarded under him, 10 post-graduation have been completed, 10 postdoctoral also been completed, and 150 undergraduate summer students are working under him till today. Personality we have in our institution. We are fortunate enough, sir, you accept our invitation to come over here only to talk to you people, to students. Once again, I welcome you to Pravara Engineering College, Loni. Thank you, sir. Thank you so much.
Now I would call upon our respected HOD sir, Dr. R.W. Gaikwad, to kindly felicitate Dr. B.D. Kulkarni sir.
Thank you, sir. Moving forward, I request Dr. B.D. Kulkarni, sir, to please present his information lecture.
Namaskar. I'm going to talk to you in all languages, including those which I don't know. If you don't follow something, you can be sure that I have also not understood. Anyway, I remember to have come to Pravanagar about 25-30 years ago, when the college was in its infancy and incipient stage. And I remember Professor Patil was the principal at the time. I came to inaugurate the student chapter of the Institution of Chemical Engineers. If my memory is good, years, maybe till 85 or so, because the college was in the process of recruiting a large number of teachers, professors for the department. And many of those professors whom I remember have recruited during those early years, today have retired and are placed somewhere around. That's what I was just talking to the principal, and he was telling me that many of these people are now retired now. There was a period in between 85 till about 2015 when I also got going extremely busy with number of assignments on my in my lab. And so despite the fact that I always wanted to come to Pravaranagar, I could make it that often. Post 2015, I am also a retired person now, superannuated. Although I continue to work at NCL as a INSA senior scientist, and therefore I am available at NCL. But then the workload is reduced. It is practically nothing. I am kind of a relatively free person, and spend most of my time talking to the youngsters, talking to the scientists at NCL, or anyone. I follow an open door policy where anyone can walk into my room without any appointment, without anything. Just sit across the table and talk to me about whatever subjects that. Are you able to hear me now? Yes. Yeah, okay. So I'm kind of an available person and spend most of my time talking to different people. They come from colleges around, they come from within NCL. We have about 1,000 youngsters. About 500, 600 of them are engaged in doing PhD programs, and another 400-500 are working as project assistants on several programs and projects. So many of the times it happens that I'm busy throughout the day because somebody else or the other one want to come and talk to me. The policy that I declared post 2015 is that anyone is free to come and talk to me with the condition that whatever results that come out of our discussions, ideas, please do not give me any credit for that. If you agree for that, then you come and talk. Because I don't want my name on any of the papers that you write. I don't want my name on the patents that you write. I don't want any credit. If it is agreeable to you, then you please come and talk. Now tell me, what do you do when you have crossed 500 publications in international journals of very high standing and repute? What difference would it make to me if I add one more to that? That's number one. Number two is that my role as a mentor in NCL now is such that I don't want the scientific community which is guiding the student to feel little uncomfortable when a bigger name gets associated with the idea, with the thing. So the student will be unhappy or will be uncomfortable in coming and meeting me because his guide would feel that why are you going to him? Because then once the ideas come from him, then we have to, and then it gets diluted. So to avoid any such kind of things, I declared it upfront in the community around that most of the people can come and talk to me for any, and then as a result, the kind of influx that I have in my room from the students is extremely large. I'm very happy about it because it gives me immense pleasure to talk to the younger people, to see how their ideas grow. And particularly in the context of the current situation in India, where a very large number of our population is under 35. I think it would make immense sense that there should be someone around them as a mentor who upfront has declared that I don't want any credits of anything that happens out of the discussions that we take place, it's all yours. So it is keeping me busy, which is what is the most important aim and objective. Well, today when I agreed to come to Pravaranagar, I do not have any topic in mind to talk to you people. If you have something that you would want to hear from me, come on, tell me that you would like to hear on these things. I would try and incorporate it during the so-called lecture. It's an open house, informal chat with you all students, and I would encourage participation from the audience in form of asking questions, because that would probably make it more clearer, and therefore we would be having, and I have no time limit. I can speak to you for an hour, I can speak to you for 1.5 hours, I can speak to you for half an hour and close, and then you can start discussion. I have no problems with any of it. There is no topic that I suggested. I said that I want to talk to the chemical engineering students and give them a perspective as if we are traveling in an aircraft, and I want you to see the ground below, how Pravara Nagar is located, where is Sangamner, where is Ahmednagar, how the roads are connected. So I want to give you an overview of how chemical engineering has evolved over a period of time, so that you get a better perspective about your own profession. Now, why I thought I would talk to you about this is because of the simple reason is that particularly chemical engineering students, I have found it through wide experience now for last 20 years that I am in touch with them, is that most of the chemical engineers, the definition as is given quite often, there are two definitions given. One is contradicting the other. The first definition is that a chemical engineer is a person who talks about chemistry where he meets engineers, and talks about engineering when he meets chemists. When two chemical engineers meet together, they talk about philosophy. That's not a very good definition. But indeed, you would find that chemical engineering students are confused in their mind about the very basis of their own profession, because as they come and join chemical engineering and begin to learn it for quite some time until they come to the 3rd year, 4th year stage, they don't know why they are doing what they are doing. Like other engineers, like mechanical engineering students, electrical engineering students, civil engineering students, when you talk to them, their focus and domains are well defined. A mechanical engineering student will learn about, because his main job is fabrication, and therefore they are the people who manufacture right from a small needle to an aircraft, but they are primarily in the domain area of fabrication. Fabrication using the materials that are available. They could be metals, they could be wood, they could be any other material that's available to them. They want to create, fabricate and create a device that is going to be useful to the society. So their role is well defined. You talk about electrical engineers, their role is well defined to provide power to the machinery so that the work can be done. Civil engineers are well defined in terms of their structures, in terms of building the dams or whatever, and therefore their domain areas are fixed. When it comes to chemical engineer, there is no domain for him. The domain is wide open and the whole universe is his domain. But a chemical engineer doesn't know this. There is a story, Marathi song, if you people know, Eka Talyat Hote Budake Pile Surekha. The chemical engineer is like that. That in this big Sarovar, he is one person, he doesn't know that he is Rajkumar. बाकी सगळे बगळे त्याला हसतात. कारण त्याला स्वतःचं रूप माहित नसतं. In a similar fashion, chemical engineers don't know their own profession because it is so vast and beyond comprehension of a normal man. The second definition, therefore, of a chemical engineer is that he is a person who is the most privileged entity living on this planet. How do I justify this? तुम्ही सकाळी उठल्यानंतर पहिल्यांदा काय करता? नळ सोडता, पाणी. Who gets you this purified water? Who gets you this water which is of a potable quality? मग्गा जो वापरता, प्लास्टिक बाटली, बादली जी वापरता, the shaving cream, the blades which have got the titanium coating on it because they will last longer. Everything that you touch from the morning till evening as you go to the bed, you would find that you are touching an object which is made by a chemical engineer. In fact, chemical engineer is always at the center stage, wherein it is he who manufactures, it is he who fabricates, it is he who decides on the quality of life of the society where we all live. Whether it is medicine, whether it is agriculture sector, whether it is energy sector, whether it is environment sector, whether it is water sector, any of these things that you take, unless the inputs from a chemical engineer is received, the final object which is used by the society cannot be prepared. The most chemical engineers don't know the central role that he plays in bringing about the quality of life to the society, the sustainability of life for the society, the transportation, the mobilities, you name it, including the safety and security. And therefore, if you look at the government agenda, you find that all of these are the most important items on any government for making the country live peaceful. The most contributions and the most significant contributions to all of these areas with which a human life is concerned are actually touched by a chemical engineer in one way or the other. The central role of chemical engineering, therefore, in the society is extremely large. But unlike the other branches of engineering where the domains are well defined for them, the domains for chemical engineer are very wide, very, very wide, and therefore beyond the comprehension of a youngster as he comes and joins the profession. It's only as he grows and becomes matured in the professional areas where he wants to work, he begins to realize the importance of chemical engineering in the everyday life, in the society around, and the role and the central role that he can play in uplifting the life of the poor people, in bringing the quality of life to the society, in everything and anything that otherwise we would do. I think that this was the first searchlight that I want to throw on chemical engineering students, that don't undermine yourself, don't underestimate yourself. Although there can be a background wherein you feel uncomfortable because you don't know why you are learning all that what you are learning. As you grow older and as you begin to solve the real world life problem, you will realize that the central role that a chemical engineer plays is extremely important. Today the world is facing tremendous problems. The problems are sustainability, because that was, I think, inadvertently given as a title. Sustainability issues are becoming extremely important. The only person who can solve the sustainability issue, maybe it's dealing with climate change, maybe it is dealing with scarcity, raw material scarcity, maybe it is dealing with energy crisis, maybe it is dealing with water crisis. The only people who can come forward and finally solve this problem, not just for the local society around, but for the world at large, you will find that the role of a chemical engineer is going to be extremely crucial. It's only he who can provide solutions to these complex problems which are evolved as a result of the society interaction with each other. I will come and touch upon some of the issues dealing with the sustainability problems. They are wicked problems. They are not the kind of problems that you can define in the form of a statement. The solutions to climate change can be good or bad. It cannot be right and wrong. Engineers are taught methodologies to provide solutions that are right or wrong. For example, that the carbon dioxide levels in the atmosphere are rising. They are going beyond limits. And people are saying that unless you take care, the earth temperature would go up by 2 degrees. And in the Paris Convention that took place in last year, October 2015, I think, it was all agreed. India was also a signatory to 190 countries who participated. That we are all agreed that we would reduce the emissions to 30% of our 2005 GDP. We agreed that we would create additional carbon dioxide sources for absorbing by increasing the green cover. All of those kind of things are given. Now, who will take care of the carbon dioxide? It's only absorption or transformation of this carbon dioxide into something called valuable chemicals, which is a perfect domain for chemical engineers. You talk about energy crisis, you talk about water crisis, you would find that the central problems which are to be addressed in each one of these themes are the domains, the real domains of where a chemical engineer can work and contribute. In England, in 1950, for example, to take care of the carbon dioxide problem, they decided that all government vehicles that will run only on diesel and not on petrol. Because petrol will give the C carbon number being more, will give more amount of carbon dioxide and therefore would enhance the temperature rise of the Earth planet quite significantly. Now 50 years down the line, they observed that while the carbon dioxide levels over England have been low, relatively low, because although we share the borders on the land, I think we share the same atmosphere everywhere. So what is there in England today may come over to some other country next day. And therefore, since we share the common atmosphere, I think people have to be worried about this. Now they observe that while the carbon dioxide ppm levels have gone down or have not gone up as much as what they would have if they were to use petrol, they observe that the NOx concentration has gone up. Now what it means is that using petrol-based car was a temporary solution valid for 50 years. It's a sustainability issue. It's a problem which is wicked. It doesn't have right or wrong solution. It has only good or bad solution. And therefore, it was a good solution that time, but 50 years down the line, the solution turned out to be bad. Sustainability problems have this particular issue with them. That not only they are good or bad, I think there is no trial and error solution possible. There is no upfront measure that you can define to say that this is going to be the solution. The perspective with which you approach the problem decides the nature of the solution. Something that is good for the rest of the world may not be good for me. And a situation like that is emerging in the IT sector, for example, wherein using artificial intelligence, where chemical engineers also contribute. They have come up with a design for a robot which will do all the job of the human mind, including thinking, and he will learn by mistakes, whereas we human beings don't learn by mistakes. If I am driving the car and because of some error, the accident has occurred, a robot will learn from that accident that in such a situation, this is what he should not do. Whereas the human people that error keeps recurring time and again, and we don't learn from our experiences as much as what that mechanical machine will learn. A time will come when probably there won't be any need for the human beings around. But it is good for the Western society because they don't have young people. They don't have enough population. In a country like India, although it may mean an advancement of science and technology, so that things are done more precisely and in a manner practically errorless, this is not a good solution for me. So sustainability kind of problems always pose you very difficult scenarios and situations wherein something that is good for someone may not be good for some other person. And that's exactly why there is a quarrel between several nations. United Nations is trying to mediate and tell people that if America and Europe have 80-90% of the carbon dioxide which is emitted into the atmosphere is coming from their technologies and science, why are you holding India responsible and asking them to cut down their carbon dioxide limits? Because if I have to grow, I need energy. If I need energy, anything that I burn will finally get converted into carbon dioxide and water. And therefore, if I am to grow, if my economy has to grow, then I have to use larger extent of energy and therefore larger extent of carbon dioxide in the atmosphere. If you are imposing the same restrictions that you are imposing on the Western nation to India, then it's a disadvantage to me. And therefore a solution which is good for them is not good for me. And therefore, with 190 countries participating, with each one having its own point of view, you would find that 190 different opinions get expressed, and therefore we don't come to a certain consensus. But India being a wise country, India being a country with large history behind it, understands that I am not looking at it only from my selfish point of view. Because finally I share the same atmosphere as the rest of the nations. And therefore, pointing fingers at you did this, and playing the blame game, we understand the central point that yes, carbon dioxide emissions must be reduced. And we would try and make our best, we put our best foot forward to ensure that we would stick within the limits. Now while the so-called intended nationally determined contributions that is called INDC, has been agreed upon. The government has gone forthright in committing itself to all of those things which are within the realm of the United Nations. The question is, how are we going to do it? How am I going to reduce carbon dioxide emission? How am I going to make sure that there is enough water available to the societies that are there without creating environmental, ecological imbalances and social disturbances? But we have done that. We have done that on the basis of you all younger people who would come up with innovative thinking, innovative ideas, new inventions, and will contribute towards the nationally determined goal in a very substantial way. In an indirect way, the government has put pressures particularly on engineering students, particularly on chemical engineering students, because the subject matter that we are going to deal with in the next 10 years, to make sure that we don't exceed the limits that are given to us, will all be provided as solutions by the chemical engineers of this country. And therefore, the role that chemical engineers has to play is extremely, extremely critical. And I think that unless we tell our students what are the challenges that they have to live up to in the next decade as they come out of their colleges, we need to initiate them. I think that here is a point where I will digress again. I will come to science and engineering education itself, and then come to the task of inventions and innovation, because that's something that would make absolutely clear the picture. Look at the science and engineering education in the country. Right from the time we became independent, there was nothing called policy of science. The S&T policy was not in existence. It came into being only in 1958 for the first time, wherein it was agreed that those people who are brainy, who want to do science, I think that they are little different people. And therefore, we must protect them, we must isolate them from the society, we must give them anything and everything that they want. We should leave it to them as to what they are doing, because they are good brains, they are intelligent people, vibrant, and therefore we should give them this security. The modern education institutions were called the modern temples of India, because it was believed that it's only science and technology which, through its implication in the society, will bring about a change in the living standards of this country. We recognized post-independence that India has been a rich country of rich resources. What is it that we don't have? We have everything that the rest of the world has. And we are a very rich country in terms of the resources. But in terms of the people who live in this country, we are living in the poverty. That's because of the imposition of the powers from outside. That we were subdued always. India lived in a poor state. State of living was extremely poor, although we were a rich country. So the new government which came after independence understood that the only way to transform this is through science and technology. And therefore science and technology was given a special status. Those who were engaged in science and technology were given the freedom, do whatever you want, remain isolated. And the hope was that we would come up with something that's useful to the society at some stage. So the government started all IITs, government started new educational institutions, new medical colleges, everything. In 58, when the policy was formed, for the first time we recognized that S&T has a very central role to play in the development of the society. Post 10 years, when a relook was taken, we observed that science and technology has given me 3 products, including engineering. One very vibrant class of people, students, who were so bright that they got better opportunities and they started looking for greener pasture elsewhere. Most of these people have left the country. They went to US, they went to Europe, they went to all over the place because the salary packages was very good. And these people were for some reason not available to the country. This was the so-called famous problem of brain drain. So much was talked about it in the decades of 70s and 80s. The second crop that came out of the science and engineering institution was people like you and me who didn't go abroad. But the hope that government had was that these people will be engaged in the public sector organizations, and the public sector companies will employ these people in the hope that the technology would be upgraded. The brightness of these students and the kind of work routine that was there in the industry, particularly public sector industry, didn't match. Most of these people were therefore unhappy working in the public sector industries, but no R&D was done because the challenge and the demand of R&D was not made on these people. The third category of people, as can be expected in any society, were little below the line kind of people who took up any kind of job that is available to them. And government thought that we must come back and do something to take care of this brain drain issue, to take care of the R&D, technological R&D. It is at this point in time that a relook was taken at the engineering education. By that time, even in the Western world, the science and engineering policies were getting changed. The Grades Commission report from the American Institute, when it came, it very categorically identified engineering education as engineering science-based education. If you look at the chemical engineering profession itself, you find that chemical engineering started in 1888 in a dilapidated, given up textile mill shed. Because in Manchester, there used to be, was the capital of all textile goods. And in one of the dilapidated, thrown away shed of this textile mill, chemical engineering was born. It was Graham Davis, who was an inspector, industry inspector. He was not a chemical engineer, but he was inspecting number of industries, and the industry friend came and asked him the question that I want to ask you as an industry person, that I am running my industry. I have a mechanical engineer who takes care of my fabrication of the machines. I have an electrical engineer who takes care of my power requirement for the machinery. I have a civil engineer who takes care of all the structures that I need for mounting my equipment and all of that kind of stuff. But I don't have a person who understands the heart of the process. The transformation process that is taking place in the plant, I need a person who understands that process, and therefore will be in a position to come and design a system, a reactor, which will give me the production without creating waste. Now this was translated in the form of 12 lectures by Graham Davis, and the first chemical engineering term was coined and used there. In 1889, by that time, during the year, 4 different departments of chemical engineering got started in America. They emanated and came out of, like the Wisconsin department came out of mechanical engineering, the Michigan one came out, there are 4, 5, 6. But during those 1 year period, 3, 4, 5 departments came up with well-designed courses wherein the central heart of the process plant would be understood, and a new branch of engineering was born called chemical engineering. Now until 1923, when Arthur Little wrote that book of chemical engineering principles, there was no document of chemical engineering existing prior to that except the notes by the lecturers who were giving the lectures. It was observed that there was some person working in sugar industry, there was another person working in paint industry, there was another person working in some other industry. And while these people were trained both for mechanical, electrical, civil, as well as to understand the heart of the process, they were adequate for that industry. But if I have to take this chemical engineer from sugar industry and put him in paint industry, he is not able to do as good a work as he was doing in sugar industry. But then the kind of operations that these fellows carry out, maybe it is crushing, maybe it is grinding, maybe it is distilling, maybe it is extracting, maybe whatever it is, the unit operations seem to remain the same. And therefore, rather than industry-based education, if we convert our education into unit operation based kind of thing, then such an engineer will be more generic and therefore will be available to any industry for its growth. That's how the first paradigm of chemical engineering was born. It's called the unit operation paradigm, wherein a chemical engineer was involved in designing the process plants at the scale of the equipment, which is meters long. Now, post 1923, after that book was written, number of advances were taking place. These advances essentially were to move from the length and time scales that an engineer uses for design from the scale of the equipment to the scale of phenomena. That when I design an absorber, I am talking about mass transfer. Now, mass transfer occurs across an interface. It occurs at a macroscopic length and time scale, which is of the order of few millimeters, few seconds, and not at the order of the equipment. And therefore, a new paradigm was born in 1950, because by that time we began to understand the phenomena that is taking place. What is it that says? It is heat transfer, it is mass transfer, it's hydrodynamics, momentum transfer. There are chemical transformations occurring which occur at a certain reaction. We realize that thermodynamics play an extremely important role because it tells me the final visible thing. It tells me certain things which are not visible. It tells me what are the domains where I can operate. Enabling tools and techniques like maths are extremely useful because mathematics allow me to look at the process, plant, phenomena, whatever that you are talking about in a completely independent manner and is the language of science. I realized that if grammar is the science of language, then mathematics is the language of science. Now this is a profound statement. And therefore, chemical engineers adopted natural sciences like chemistry, physics, biology, whatever that is required. We adopted engineering as mechanical engineering because we need to do fabrication. We adopted power, electrical engineering. We understood the role of civil engineer and therefore incorporated it in our study. We incorporated the phenomenology of the events that take place at the macroscopic level so that the length and time scales at which I should design my equipment became clearer to me. I incorporated mathematical tools of prototyping, designing system through sets of equations and therefore raised the level of a chemical engineer from that of a plumber's kind of job to one of an engineering science person. And this science person was so powerful that he could talk to the chemist shoulder to shoulder. He could talk to physicists shoulder to shoulder. He could talk to biologists, he could talk to mechanical engineers, he could talk to electrical engineers, he could talk to civil engineers. He could talk to instrumentation fellows, he could talk because he has mathematics as the basis of his understanding. And therefore became all-powerful person now available at the center stage. Post 1950, the marvelous development that took place is phenomenal. If you look at the raw materials, for example, post 19th century, in the early 19th century, it was all from the bio-based raw materials, like soda ash. Why has that name ash comes? From where does it come? It was the marine biological plants which grow all around, which have got large amount of salt in it. Now literally this plant was burned to create the ash. It was dissolved to remove that ash and was reprecipitated as what is called as the soda ash because it had detergent properties. So the first soda ash plant came from biological sources. If you look at until 1950, even all colors and dyes were made from biomaterial. The material that the color that you use during Holi, for example, is all derived from plants. So plant was a basis, a raw material for making number of different products that the society needed. And it was chemical engineer who was transforming these bio raw materials into useful material for the society. But post 1930, coal began to emerge as an extremely important raw material. And till 1960, when petroleum completely displaced coal, all the chemical processes and plants were based on coal as raw material. So right from town gas to anything and everything that you look between that period, you would find that the coal-based chemistry, including Fischer-Tropsch synthesis. South Africa has the largest plant for producing diesel and petrol aviation fuels from biomaterials, from coal, the fossil fuel-based energy, the Sasol plants, which became famous in the world, actually all are derived from the coal biomass kind of thing. Post 1960, petroleum was displacing everything, including coal. And the crude that we get has changed the entire game so substantially that at post 1960, development of things like polymers and a huge difference that the polymers have made, because it became one of the material available to the society, that I don't have to use steel, I don't have to use wood, I don't have to use many things which polymer plastics can do. And therefore, post 1960, million tons work plants were designed by chemical engineers to crack this crude oil, transform them to platform materials, and through the use of reaction engineering, through the use of controls, through the use of dynamics, through the use of optimization, through the use of multi-criteria decision tools, with the use of life cycle analysis, we were able to come and design our processes and plants that changed the world economy substantially. Who did this all? It's chemical. It is he who is manufacturing material in millions of million tons, and not just one chemical, but thousands of them, which are useful to the society, and therefore the role that a chemical engineer plays in the society is inimitable. Nothing can beat it ever. Coming to the third category, the phenomenology based designs that chemical engineers did post 1950 till almost 1980-90. We came to a stage where, given the raw material and given the product that you want to make, in less than 2.5 years time, I can construct a full scale plant. Because Aspen-like tools were available to me, process flow sheeting could be done, process scheduling, anything and everything that you want now could be done at such fast pace, imposing thermodynamic limits, designing controls, designing optimizers, everything was done, and in less than 2.5 years time, a process plant can be built. We thought that it's the end of chemical engineering, very saturated, very matured area, and we will be able to deliver in no time. The moment makes the society make the demand. But post 80, the situation changed again a little, and we entered the so-called third paradigm of chemical engineering, which is the molecular chemical. Now, when it came to pharma industries, where the drug molecule has to be very specific, it's a very complex entity in structure, but by making a small change in that structure somewhere, if I can generate a new molecule that's going to be a savior for major diseases like maybe TB, maybe anything that you name, then I need molecular engineering. I need tools and techniques which will allow me to probe not at the micrometer length scales, but at the length scales of molecules. And the density functional theories, you name it, chemical engineers acquired all that knowledge for the molecular chemical engineering, and new functional materials, adsorbents, catalysts, pharma products like drug molecules, or any other specific molecule which has special attributes required. We were in a position to come back to the third paradigm. So post 80, chemical engineering has again diverted from the second paradigm of phenomenology and macroscopic length and time scale modeling to a new set of further pruned it. Further, we went from the equipment scale to event scale, from the event scale now to the molecular scale. And all the tools and techniques that we need for analyzing such chemical engineering and eventually incorporating them in the design was finished. When, during the last 2 to 3 decades, while we have acquired all these tools at different length and time scales, we are thrown back onto the scale of the planet because of the sustainability problems. Now, chemical engineers are today working in the paradigm of sustainability, wherein while they have to simultaneously take care of the events that occur at molecule level, integrate them to macroscopic length and time scale, integrate the whole thing to the scale of the equipment, and as if that is not enough now, I have to go beyond the scale of the equipment to take care of the planet. A typical chemical engineer, given the factory, was limited to his inlet door where all the raw materials come and outlet doors where all his products go out. He didn't bother about from where the raw material comes. As long as he makes a demand, pays for it, the raw material is delivered at his doorstep. The products are picked up from the factory outlet. They go into the market, he makes money. So the definition of a chemical engineer enterprise was limited to inlet of his factory to the outlet of his factory. Marketing, distribution, taken care. But now when I tell you that if I have a boiler in my plant and if I am burning wood, then a chemical engineer must realize that the raw material is not wood. He is not burning a log of wood there in the boiler. He is burning a tree in the forest. So the limit now extends from the inlet gate of the factory to the natural resource from where I get my raw material. Similarly, when the product from my outlet goes out, it goes to the market, gets consumed. After its consumption, the remnants are thrown away as waste, and I am accumulating very large amount of waste on the earth planet. If I am the one who is creating, then I am the one who is also responsible for its disposal. No other profession ever will take this view other than a chemical engineer. Because my limits are not factory inlet outlet. My limits are the natural resources from where I draw them. Finally, to those natural resources which I return to the Mother Earth planet to make sure that its composition, its health remains intact. Because one of the definitions of sustainability is that if I am enjoying the fruits of what Mother Earth has given me, I have every right to consume it. But I have no right to erode it to a level wherein they are not available to the next generation. The role can be played only by them. Therefore, whole system analysis, multi-criteria decision analysis, multi-objective optimizations, extending the limits of my factory and the realm of my profession beyond designing only within the inlet outlet of the factory, I have now to create designs which will incorporate beyond the factory limits the natural resources from where I draw it, finally to the waste that I return to the motherland, so that everything is conserved. Therefore, the objective of chemical engineering profession is from end to end. The whole planet is my home. I cannot destroy it. I, as a chemical engineer, if it's using the resources that are available on this planet for my use, I have every right to use it for the society. But I have no right to consume and erode it to a level where they will not be available to the next generation. So the profound objective of the profession then gets defined and very well placed. We are moving into this fourth realm of chemical engineering, where while designing, I want my engineering students to incorporate the thinking of sustainability in their design and not design it just for the enterprise inlet outlet. To maximize the property of the entrepreneur is no more the single objective. Maximizing conversions of raw material is an objective. Green chemistry, green engineering, process intensifications, multi-objective optimizations, criteria decision analysis, all of these have to therefore become a part of my profession so that I can serve this Mother Earth planet better. I think I will stop here and allow you people to raise questions and feel free to raise anything that comes to your mind. Thank you for it. Was that adequate time, or you wanted to hear more, you wanted to hear less, whatever?
So, in construction of road,
Yeah, just one thing, do not hesitate to ask any question. Because our knowledge, our sphere of knowledge is so much less than our sphere of and therefore something that might appear stupid actually will not be so. Because all of us are ignorant. One thing in common that we share with each other is the extent of our knowledge. And therefore do not feel hesitated, do not have any hesitation about asking any questions. Just feel free. I may not be able to answer all the questions, but I will try and at least give a perspective to the question that you
so in construction of road, we use plastic waste. By treating that, we use in construction of road. My question is, medical waste, how can we treat?
I think currently medical waste is treated using the plasma reactors. Primarily, in treating medical waste, the main problem is the contaminant. And we cannot afford the contaminants to grow into the society where it can cause a lot of damage. And therefore, complete destruction of medical waste is essential. I think today they are coming up with a number of different technologies, but then the plasma-based reactor technologies are more common. These days, even handheld plasma torches are available.
Thank you, sir.
Yeah, just open up. This is an informal talk. As I told you, the trend. Yeah.
Sir, how as a student can we contribute sustainability in our workplace?
No, I didn't understand the question.
How as a student can we contribute towards sustainability in our workplace?
I think the first thing is to change the mindset. What I told you today is not what I generally talk to you today is not the mindset of chemical engineering therefore we need to change the mindset. What does the chemical engineer do? He comes and designs. He designs a process plant for large scale manufacturing. Now while designing the plant, if now he starts thinking to incorporate the sustainability issues while making a design on the table itself, then the sustainability issues will be taken care of in the course of time. I think I did tell you about the difference between invention and innovation, and it's particularly important for the younger people now. One needs to understand very clearly the nexus of science, engineering and technology. Now, in the common parlance and layman, these words are used interchangeably without understanding the specific role that each one of these science, engineering and technology plays in the society. Now, science is all about understanding the fundamental laws of nature. We want to undermine the mechanisms through which certain things happen. We want to understand and develop a fundamental knowledge about the nature itself. Now, science doesn't care beyond that. It will come and tell you that if I take 100 gallons of water from sea, I can extract 1 milligram of gold out of that. But then, that's not the domain of engineer. The engineer wouldn't agree for this because he will incorporate also the engineering designs in it and say that if that 1 milligram of gold is going to cost me 10 times more than what's available in the market, why would I put up a plant? So there is a practical angle when an engineer sees it. But science doesn't worry about it. It wants to undermine the fundamental laws of nature. It wants to understand the underlying mechanisms and is largely curiosity driven. Engineering, on the other hand, wants to make use of the science discoveries and convert them into something large scale manufacturing which the society would use. I'll give you an example. That at the electric bulb, for example. Now Thomas Alva Edison is credited for the bulb, and now he was not the first person to pass current over wire and generate the light. The science of this was all known around that time. What he did was that he usefully converted this knowledge of science. So he designed a glass bulb around it, creating an environment. He put nitrogen in it so that the oxidation of the film will not occur. Because prior to that, while that wire will emit light, it will get oxidized simultaneously and therefore will break. Now, all of these practical difficulties were overcome, and he created a bulb which is a convenience to the society, and therefore society is willing to pay for. Nobody is willing to pay for science. It's curiosity driven, it's a hobby. And therefore, except for government, Rajashraya असल्याशिवाय science चालू शकत नाही. Because it's only curiosity driven. But engineering, we convert the invention, discovery, through innovation, into a practically usable gadget which the society would use. Engineering therefore does a very useful thing of converting inventions and discoveries into innovations. Innovations by themselves may not be very original. They may be based on the science discoveries like electric bulb I told. Or Ford was not the first person to put the vehicles on move. Alex Bell was not the first person who passed sound over wires to create telecommunication. The facts in basic sciences were already known and well established. But these people converted the basic fundamental knowledge that was generated in science through engineering skills to gadgets and equipments that the society needs and is willing to pay for. So there is a difference between invention, discovery on one hand, and innovation on the other. Now innovation therefore being not very original, but are based on some original observations. So science comes up with all kinds of new discoveries, like buckyballs, the structure of carbon, which actually won the Nobel Prize. But when you look at buckyball itself and its application into the society, you find that it's almost a useless material. I mean, during our times when we were children, when a child is born at home, they will take a chimney and burn some well-defined oil with a small flame and cover that flame with a glass plate. The black soot that gets deposited on the glass set is actually buckyballs, is that carbon. But then the practical use of buckyballs is practically nothing. So it is not, this is one invention you cannot convert into innovation. I'll give you another example. Seawater, for example, saline water. The water is such an important thing that in a city like Madras, they have a huge coastal line, abundant water available but not water to drink. Can I not desalinate this water and create potable water? All that it needs is energy input into it. If I take a glass of water and put some common salt in it, it dissolves. And during the dissolution process, we chemical engineers understand that there is a heat of dissolution involved. Now thermodynamically I can calculate what that heat of dissolution will be. So in theory, if I want to dissolve that, I need to put back that energy which was the heat of dissolution into that glass of water so that salt will separate. Now if you look at thermodynamically desalination, it costs you something like 0.75 kilowatt hours to treat 1 cubic feet of water. We have large MSF thermal desalination plants in Abu Dhabi and the coastal line there because they have energy cheap. So they use thermal power to dissolve the seawater and create potable water for them. The amount of energy they spend is 5 kilowatt hour. Thermodynamically I require 0.75. Practically they are using 5. So people came up with membranes. They said that why use thermal energy like this? Let me use reverse osmosis. Reverse osmosis has cut down the energy requirement from 5 to about 2.2 kilowatt hours to treat 1 cubic meter of water. Now, if you analyze as a chemical engineer that 2.2, you find that at about 1.3, 1.4 kilowatt hours actually is required for other than separation process, like pumping the water through the pipeline, to work up the friction, to have the pipeline neatly networked and connected. So what it means is that for separation purpose I am using about 0.8 to 0.9 kilowatt hours. Rest is all used for mechanical operation. Now I cannot do anything there. As and when efficiencies of those units will improve, it's fine. Otherwise, from a chemical engineering point of view, I have come to 0.8, 0.9 and thermodynamic limit is 0.75. So if someone comes to me saying that I want to design a membrane that is thinner, tougher, whatever, and will therefore require further less energy, I'll say that yes, okay, I agree with you from principle. But economically will it make sense? We are already at 80-90% thermodynamic efficiency. Now by doing this extra innovation and spending time, effort, money, the return on your investment is going to be very small. So while you might do whatever you want, from an innovation angle, this is not a good example to innovate. So innovation is emerging out as an extremely new area, and particularly for the younger people, wherein innovation is what we are talking about. In the 2013 document of the government on S&T policy, for the first time they have introduced this word innovation. Because until now it was all science and technology and all that it encompasses. We were saying that should be a part of our S&T policy, so that we improve, we improvise, we bring up our poverty lines, all of that. Actually, innovation is a completely different dimension than invention. And I want my younger people today not so much in the invention and discovery area. Yes, they are extremely vibrant, very powerful. But then 90% of my younger brain power, I want to be utilizing it for the innovation and come out with something that is scientifically correct, technologically correct, useful to the society in an economical, environmental and social context, so that society gets that. And this doesn't require me to do very, very high science. There are already existing science, like this water example I took you. That everything is known, thermodynamics is known to us for last several years, membranes have been prepared. So if someone comes to me and says, I want to develop a new membrane that can separate water and salt, I tell him that, young friend, don't do that. There is nothing that you will get into. Now if you analyze in the same context, all the problems that the world is working over for the last decade, you find that all of those problems are useless problems, and we should not spend any money, time, effort in doing any of them. What are those problems? I think I began with starch and wanted to convert it into ethanol. It is the most stupid thing to do. Starch is such a wonderful molecule that I can do so many other things with it. Why am I creating that ethanol? A very low energy efficient fuel. Also, in doing so, I was consuming natural gas, petrol, diesel in the form of energy. Now, do you think that it makes sense to degrade high-level energy into low-level energy like ethanol? It doesn't make any sense at all to an engineer. It doesn't require very high, bright science. You can use your common sense and say that it's not good. So the first generation biofuel program is out. Also, government would not have allowed you to use eatable material to get converted into energy like sector. Then we moved from first generation fuel to lignocellulose. Here it's a waste we burn as fodder, we use it as cattle feeder fodder. Lignocellulosic ethanol is a gone case. It's not economically viable. I don't know why people don't understand such simple things. Say, lignocellulosic material, bagasse for example, cane sugar crushes it all around, throws away that bagasse, burns it in the boiler. If I have to convert that bagasse into liquid fuel, one, the energy density of this material is very low. I mean, per ton of that material when I burn, the amount of energy that I get is very low. Number two, the density of that material is also very low. So if I have to carry 1 truck load of bagasse, it may come to 4 tons, 5 tons. But in the same truck, if I am carrying a gas or if I am carrying the energy density being high, I am carrying a much larger energy source than carrying the bagasse. Now 50 kilometers is the radius within which if this raw material is available, I can erect a plant. Because the economy of scale is extremely important. I cannot put a 5 ton per month plant, 10 ton per month plant. It's not going to be economically viable at all. But if I want 1000 ton plant to be put up, where is the raw material? Within 50 kilometer radius, if I don't have bagasse, I cannot bring it into the plant. And to bring it anything outside 50 kilometer limit, my transportation cost is very large. So it doesn't make sense at all to convert bagasse into lignocellulose. The third generation, which people were extremely kind of hopeful about, was these algae and macroalgae. Now there are companies in the US who have been generating something close to 90 lakh liters of the algal biomass for crushing to produce biodiesel. At that scale, it's not viable. Because photosynthesis being the main crux there, those who understand and chemical engineers who understand what photosynthesis is, the energy efficiency of converting light first into the biomass and from that biomass finally into the liquid fuel is economically advisable. Now while 100 crores of rupees are spent in the country and several million hundreds are spent world over in trying to generate alternative fuel source other than the fossil fuel source, you find that a rigorous engineering analysis of all of these problems will drive you to the conclusion that they are economically unviable. Now the final question, holy grail that people ask. Carbon dioxide is emitted, we are worried about carbon dioxide. Can I convert this carbon dioxide into chemicals? Yes, soda ash is one, urea is another. I need several such million tons. But then I am throwing away gigatons of carbon dioxide. I mean, less than 0.00001% is only I am utilizing. So if I can convert this CO2 to methanol, now this fellow Ola, he got his Nobel Prize for converting carbon dioxide into methanol. It's such a fundamental discovery of importance. But engineering wise, when I start looking at methanol from carbon dioxide, I find that even if I give you electricity free, your electrical demand is free. Now I give you carbon dioxide, convert it into chemicals. Its thermodynamic calculations and economically viable calculations show you very clearly that this is a non-profit proposition. Nobody will touch it. Innovation and inventions, therefore, are two sides. And anything science tells you about the possible. Yes, this is possible. They will come and tell you that CO2 can be converted to hydrocarbon, CO2 can be converted to methanol, whatever you want. But engineering analysis, when you do, you find that that is the most stupid thing to do. And therefore, inventions and innovations have to be analyzed with a different frame of mind. And while I may seem to paint a little bleaker picture on the problems that the current state world people are working on, I will tell you 100%, because as a true chemical engineer who understands thermodynamics, who understands economics, who understands the environment, who understands ecology, I will tell you that these are infeasible processes. Therefore, younger people, when they come up with propositions for innovation, you need a mentor who would analyze it for them threadbare and tell him upfront that do this, don't do this. Because our population is very large and we are now gearing up our younger population towards innovation, having a mentor around with whom you can go out, talk, exchange freely, listen to his views is extremely important. Without that, we will end up corrupting our younger generation. Because they are in a state at the moment where they are productive, they are effective. If I consume their time in efforts which are not going to lead to anything, not only those people will get condemned, but nothing will be accomplished. So we have to be extremely sensitive on the younger generation and the innovations that we want to bring. I think I digressed from your point, but I hope I may have covered something that I didn't talk during the lecture. Come.
Then one time, if water is full totally, then is that possible to remove water at the middle and how?
I don't follow the question.
So consider one tank, and the water is totally full in that tank. Okay. If we want to remove water at the middle water tank, at the center water. टँक मधलं एकदम मिडलचं वॉटर आपल्याला बाहेर काढायचं.
तू एक टँक घेतला त्या टँक मध्ये
पाणी भरलं फुट आणि एकदम सेंटर मध्ये मधातलं वॉटर बाहेर काढायचं आपल्याला टँकच्या. तर ते पॉसिबल आहे का? कोणत्या टेक्निक काढू शकतो आपण?
काय पॉसिबल आहे? तिथे ड्रिल कर एक पाईप लाव.
नाही आपल्याला कॉन्सन्ट्रेशन जसं मेजर करायचं वॉटर आपण टेक्निक आपण हाताने पण ते काढू शकतो. बट ठीक आहे सर, एखादं सोल्युशन आहे एक.
Solution has to be tackled completely because water may have soluble components of the polluted material available in the environment. You need some absorbents on which those impurities will get absorbed.
Sir, whenever we talk about sustainable development, basically like कॉमन में ऐसा जनरल में बात करें तो वर्ल्ड में एक ही चीज़ है कि वी वर्क ऑन द प्रोडक्ट्स, कि हम लोगों ने इलेक्ट्रिक कार बना ली, इलेक्ट्रिक बाइक बना लिया या फिर कुछ और. सर व्हाई डोंट वी वर्क ऑन प्रोसेसेस?
We work on processes.
इको फ्रेंडली, लाइक नॉट एग्जैक्टली जो
यार
सोलर एनर्जी हम लोग नहीं बोलेंगे सर.
यार तुम ठीक से सुना होगा तो मैं वही तो बात कर रहा था आपसे कि सस्टेनेबल डेवलपमेंट हैज टू बी अ पार्ट ऑफ केमिकल इंजीनियरिंग डिजाइन. So unless I am introduced to sustainable development, chemical engineers will not incorporate it in their design strategy. तो वो तो करना है हमें.
Exactly, हमें वो करना है, but are we doing it appropriately?
No, we are not doing anything about it at the moment. World over, people have now risen to this fact, particularly during the last decade or so. In fact, there is nothing called sustainability engineering. I have introduced sustainability engineering as a coursework for chemical engineering for the first time almost in the world. दुनिया भर में कोई नहीं करता है जो हमने यहाँ किया है. अभी now it is about a year that course is running. We are developing that course for chemical engineers so that my chemical engineers will be now better trained for sustainability science.
So sir, you have been saying कि हम लोग को thinking बदलना चाहिए. सर इफ एट ऑल हम लोग अगर जैसे अभी हम लोग यहाँ पर जितने भी हैं, अगर हम लोग अपने तरफ से कुछ अगर किसी का पॉइंट ऑफ व्यू चेंज करना है तो वो हम लोग कैसे कर सकते हैं?
बस एक दो देयर आर आई थिंक द बेस्ट वे टू ब्रिंग अबाउट अ चेंज इज टू डू थिंग्स एंड लेट पीपल रियलाइज द इम्पोर्टेंस ऑफ व्हाट यू हैव डन. दैट्स ए इनडायरेक्ट साइलेंट वे ऑफ ब्रिंगिंग अबाउट अ चेंज. दूसरा चेंज उस बात से हो सकता है wherein some authoritative person comes and directs and tells you the pros and cons of making a change. Now नरेंद्र मोदी जी इतना चिल्ला के कह रहे हैं लेकिन माइंड सेट चेंज हुआ क्या? This is a problem with the so it takes its own time. The best way is in a silent way. We are not political people. In a very silent way, we should bring about a change in the society. One thing that we noticed is that the society accepts anything that is useful to them without questioning. And therefore, we should be the silent workers who are bringing about a change in the society without even the knowledge of the society that the change has taken place. No opposition. But if you go and tell somebody directly to do it, वो आपसे ये कहेगा कि तुम खुद को क्या समझ रहे हो? That's the difficulty. Changing mindset is a different problem. Yeah.
Organic farm is one of the cure for one of the ways to cure sustainability. It's one of the ways. But the organic farming, if you see, it's completely costly compared to the conventional farming. So what would you like to say about it?
Yeah, first of all, there are debates on this issue that whether organic farming, when you do the complete life cycle analysis, it doesn't work out to be, see there are three important angles. The first is the economic angle. That if as an investor I have to invest in something, I look at it as a business proposition, wherein I will calculate my input, the investment, the utilities, the expenditure that I would need to transform this input into final output, and the revenue that I generate by selling this output, so that my business proposition must remain economically viable. Otherwise, I will not invest my money because I have several other options open. So, economic viability is first extremely important issue. Legislation will impose conditions and constraints from the point of view of environment, because it is the environment and the society, it is the society which will suffer if I am doing something which is not environmentally tangible. Socially, it must be also relevant. Like if I come up with a process that will convert animal fat into some cheese or whatever like material, I will not have cultural acceptance. That I have developed a process which is economically viable, I have developed a process and taken care of the environment, but society will not accept it culturally because 90% of our society is not non-veg. They are vegetarian people and they don't want to change to non-veg. And therefore such a product will be unacceptable. So social, cultural attributes are extremely important in developing a process, a manufacturing plant, a product, because it's finally the society which consumes. Now organic farming, I am hearing different views on it. That besides the cost, because people are willing to pay premium if they are getting something in return. So people don't mind paying 15 rupees for buying a methi ka gaddi. If the normal is available at 10 rupees, they will say that it's okay, I pay 15. But then it must guarantee me that I have positive attributes of this organic farming. So economic viability to a certain extent can be absorbed, compensated. But other issues, particularly the environment, are dangerous to calculate. And unless you do the complete life cycle analysis, like Goshala is an extremely good example. That while we all talk about Goshala and the importance of it, the amount of carbon dioxide that is emitted from the vegetarian is extremely large. So when you calculate the environment damage, when you calculate the social impact, you identify the problems of innovation. And unless this analysis is done, a person should not take up an innovative problem. If he is having some innovative idea in his mind, he should first get that analyzed on the basis of the life cycle analysis, whole system approach, use all kinds of tools to satisfy the demands of the economy, environment, social requirements, then find out and prioritize the problem where he has to go and attack so that it becomes positive in all. That's where the innovation is, and is one step distilled over the innovation.
One more question I want to ask is, because the students are here and they will be working on their projects. So what kind of research area should be worked on? Whether industrial research oriented or general research, would you like to
I think at the institute level, at the college level, I don't see, I don't want to discriminate between one type or the other. But what I want to definitely impose on the department is that it bring about sustainability thinking during your course curricula in chemical engineering, because that's going to be the order of the day in 10 years from now. I mean, the government will not allow you to design a plant and operate it if environmental clearance is not there, if socially relevant issues are not taken care of. So things like pharma industry, the amount of medicines that we manufacture and actually use by patent and the excesses. The doctor gives me a strip of 10 I use 2 tablets, 3 tablets, I start feeling better. I say, why medicate you sell more? I don't need it. So that strip is the basic. All of these strips end up on the dust, on the dumps somewhere. They are leached over a period of time during the rain, during the heat. They undergo all kinds of climatic variation, and are finally leached and are put into the aquatic sources, from where people pick up all kinds of diseases, disorders. Now the social relevance of this pharma making, if it is incorporated appropriately, then I can, as a legislator, a decision maker, come back and tell that factory that your production limit has not to exceed this. Because ciprofloxacin, for example, is now a very big nuisance. It's one of the most common antibiotic wide spectrum medicine given for various disorders. And 70-80% of that is actually available in the dumps afterwards. And therefore are creating problem of a kind different. So, socially relevant problems, environmentally relevant problems, economically viable problems, all have to be combined into a complete whole system analysis. That will come and decide on the innovation that I have to make. Because today my younger people are groping in the dark. They don't know what to innovate or what will lead them to an innovation. Number 2, they do not know if an innovation has occurred. They don't have the capacity even to appreciate and understand that, hey, I'm getting something different. I can convert this into a value addition proposition. Most of my people are ignorant to a level where they don't even know if an invention or an innovation has taken. I think I need to change this. If I have large population which is in the younger community, then the sensitivity of this problem is even more. And therefore, very intent efforts have to be made to transform this situation. I am going around telling people to change their mindset. Not that in one lecture everything will be appreciated, understood, and people will begin to implement, but somewhere at the back of their mind, they will carry these notions. And anytime, anywhere they get an opportunity to exploit it, they would want to do it for themselves, they will also want to do it for others. So we are making a beginning of a change. And in this particular aspect, we don't lag behind anymore. The rest of the world also has started looking at this problem from this perspective. So why not catch up with them right now? Why is it that I have to listen to what the US fellow says or a UK fellow says? Can I not say something for the first time? It's possible with the kind of brilliance that I have in my class. It's that it's bottled up. It's not effacing. I want to give way to that. That's why I came and said that however stupid your question may look like, don't worry about that. Come out. Come out in the open to state your question problem is extremely important. Because we bottle them up. We don't allow them to ask questions, which is the wrong thing to do. Students also have grown up with that culture that don't ask the teachers. वो बाहर दोस्तों में बात कर लेंगे वहाँ जो पता चलेगा चलेगा.
So one more silly question is that you all for you. But does with artificial rain that we do, is it maintaining that sustainability?
Artificial
rain.
No.
It's not maintaining.
No way. I mean, you cannot create rain.
Yes.
What is artificial rain? I mean, the water and the humidity is all existing all around. I am conglomerating that into dews and droplets. I do it through the process of sortation. It's a chemical engineering operation, isn't it? But if I have the cloud, if I have the Akash, where there is no humidity to a level where it can be all agglomerated together, then how will the rain? Didn't you know about those failure experiments? The people spent 5 crore to an aircraft and अरे बाबा first check the humidity ना कितना है उधर पानी नहीं है तो कहाँ से आएगी रेस? So those are all hypes. I think the problem today is that in science and engineering world we are living on hype. Like hydrogen economy, it's a very big hype. Today making hydrogen on board in the automobile cars is possible. Not that the technology is not there, but we cannot convert that to a hydrogen economy sheerly because of the fact that the insurance companies who insure your vehicle for any accidents and damages will be unwilling if you tell them that you have hydrogen on board. तुम बोलते हैं चला बॉम्ब वहाँ रखा है, तो you are insuring me, you want to insure me. The whole hydrogen economy is going to be a failure in the course of time. Biofuels is going to be failure in time. Algae are going to be failure in time. Transforming carbon dioxide into any valuable chemical is going to be failure in time. It might appear very pessimistic. It is not pessimistic. It's based on the thermodynamic analysis. It's based on understanding the engineering science issues that are involved there. That as a illuminated person, you are coming and telling that is not possible. I think one should take it seriously because we are spending millions and millions of dollars. We are spending large amount of money engaging people at their time. So I don't want my younger people to spend their time for 5 years trying to create an innovation that will not finally materialize. Not only he has lost his 5 years revenues and the family needs, because in the process you have to sacrifice. You are not employed anywhere and so you are spending money from your own pocket. And at the end of it, when you find that you are doomed, the fellow actually goes down the line, he never comes up. Now, how serious is this issue? The sensitivity of this issue must be understood by the government to the last decimal. I will do my part as a person who understands this topic and area and trying to generate this area in the country. Wherever possible, I'll extend that help with, as I declared upfront, no credits. I don't want to be credited for helping it. It's your luck, you are one ahead. Any other question?
What industry want from new fresher engineer when they are taking?
I think they are already declared you as unemployable.
Many of the students have a distinction, but they are not selected. Now, one company is come for the campus interview, but many of the students are not selected.
I think this is a fallacy and an unfortunate situation. I don't know whom to blame it. Is it the education tradition, way that we come up? I have no idea. But the fact is that there is a disparity between what we teach our students and what the industry needs us. Now, industry, when they employ you, many of these industry people come and tell me that sir, we spent years on these people, training them, reorienting them, hoping that they would be useful to us now, at least having spent 2 years in the company. And by that time, the fellow has gained enough experience that he is picked up by somebody. So I end up training people and not utilizing them for my own production, my own manufacturing. I think that this is a serious issue which must be seriously thought about, and a certain kind of a meeting between the engineering education institution, the industry needs have to be posed together, interrelated, and made clear before. It's not so both industry as well as the educational institutions must come together, join hands, form a network, identify the problems that, and the faculty also then reorients itself to address those concerns and issues. At the moment, I realize that this is a serious problem.
Sir, I have one question. One more question. We are talking about CO2 emission. I have one idea that the vehicle which we are using, the silencer, inside the silencer, we form the adsorbent layer. So that
will form what?
Adsorbent layer. Adsorbent layer. So that we can reduce the amount of CO2 taken out from the silencer.
I mean, while the idea seems good, it has to be threadbare analyzed. For example, what is the saturation carrying capacity of an adsorbent?
It can be used or not.
It's not high. And the amount of carbon dioxide that you emit in terms of moles in presence of other unburned material, carbon dioxide, hydrocarbons, nitrogen, the saturation, the kinetics of absorption of carbon dioxide, it's a multi-component absorption problem. That I have CO2 there, I have CO there, I have nitrogen there, I have unburned hydrocarbons. All of them will go and compete for the same site to go and occupy. Okay. Now 1 in 4, the carbon dioxide will get only 25% charge, unless your adsorbent is specific to carbon dioxide and non-specific to other materials. That's number 1. And therefore the absorption rates are very good. The speed at which the exhausts are thrown away, the residence time over that adsorbent is the time of absorption. If during that time carbon dioxide doesn't get absorbed, then it will still come out.
Another is some barrier if we are put inside the silencer.
Barrier
means some barriers will.
No, it will create a pressure drop. That pressure drop will get translated to the engine. The three-way catalysis that people are using, it has become commercially now visible, and there are several cartridges of the three-way catalysis in the exhaust pump, in the exhaust pipe. They convert primarily carbon monoxide into carbon dioxide, because carbon monoxide is more dangerous. It's a highly reactive molecule, unlike carbon dioxide, which is a dead molecule. Because when the oil will end, there would be two things on the Earth's surface. One is water and another is carbon dioxide. Because anything that we burn gets converted finally into carbon dioxide. In our metabolic system, living system, while raw materials are used as nutrients to generate materials, the energies that we need, final product of it is all in the form of carbon dioxide and water. And therefore, a very encouraging proposal is that if carbon dioxide and water are going to be the end product of every process that we otherwise conceive of, then why not begin with carbon dioxide and water and convert that into chemicals? Come to platform chemicals, from there you will make anything and everything. And people are working on it, but carbon dioxide is such a dead molecule that you can't do much with it. So while the idea is good, it has to be examined very carefully on engineering science. And on the face of it, the problem that I see is one, the residence time of the exhaust gas or the catalyst bed or the adsorbent bed is not enough for all carbon dioxide to be absorbed. That means the kinetics of the process is slow. Number 2 is, so you have to design an adsorbent where the kinetics of the process is high. Number 2 is that it's a multi-component adsorption problem. So how will you eliminate other gases from getting absorbed, reducing that CO2 rating? The third thing is that the adsorbent has got a saturation challenge. That if I have 10 grams of adsorbent kept there, how much of carbon dioxide will you absorb? 10 grams, that's on the highest one. It will not absorb more than 1 gram. But then even if you take the complete limit, 10 gram carbon dioxide absorbs 20 grams. So, practical viability of it also has to be. Now, no idea is worth throwing away. If you have that idea, think about it. What I have raised are engineering science issues that are associated. If you can overcome those, you can convert this into an innovation. No problem on that. But then it must be otherwise. That's what I am trying to make a point. That inventions, to get them converted into innovations, requires the process of engineering analysis, synthesis, and complete understanding, so that it becomes possible. 99% of the inventions you will find here, they are useless, they are good for science, not good for engineering.
Thank you, sir.
Thank you, sir, for such an excellent expert lecture. Now I call upon Professor S.B. Magar to conclude the function by presenting the vote of thanks.
Good afternoon, one of all. Respected Dr. B.D. Kulkarni sir, respected our HOD, Dr. Raipur sir, Professor Garad sir from Chemical Department Polytechnic and his colleagues, my faculty members and dear students. It gives me immense pleasure to give out of thanks to all who supported directly and indirectly to success this event. So I take this occasion on behalf of Chemical Engineering Department at Pravara Engineering College to give special thanks to Dr. B.D. Kulkarni sir to come over here and spend their time and given valuable information on chemical engineering. So I am going to say some word. So chemical engineering. So we are talking generally about role of the chemical engineering, but main role of the chemical engineering is that so we have to decrease the burden on the Indian nation economy. So for that purpose, we are going to see sustainable process, which sir has discussed with many examples. So that when method is sustainable, so there will be a reduction in pollutants, so impact on environment and whatever the human being effects, that will be reduced. And really, sir has given many of the examples, many of the process, how this green concepts should be developed in the industry. So I promise that, sir, our students will do work on this, and sir has also told that innovations and invention. So our students will forward with your discussion. So I thanks sir to given this lot of informations. So I will going to share something along with sir because of I am interested to share these things. So hand in hand we go together, hand in hand we sing along. Side by side we face the music. Win or lose, we always sing a song. Wave the flag, when keep it flying till the sun shines over the land. So when you are amongst with us, so I can proudly say that so our chemical engineering department is proud, lucky to interaction with NCL people. So we have always guidance from the NCL scientists so that our students get more benefits. So thank you sir for your valuable guidance. I take this occasion to thanks all of my faculty members, and especially for our HOD Gafford sir, who is always taking efforts to arrange such eminent lectures and giving benefits to the students. I also thanks to Professor Garad sir, who is coming here to spend time and for this occasion. I lastly thanks to all our volunteers and our chemical engineering students. Thank you. So I will going to say one thing that for Dr. B.D. Kulkarni sir. So we are always attraction towards celebrity. So when celebrity is there, we are attracting towards him. But I am saying that so our celebrity, our chemical engineering celebrity is the Dr. B.D. Kulkarni sir. Thank you, sir.